you make that distinction. All right, so humans are doing all kinds of math. 1,500 or more years pass. We're into the Middle Ages. We start getting into quadratics, right? The quadratic formula, doing algebra. So, most of you at this point, because of what we've been doing recently, would see these two equations and you would solve these lickety-split. You would say, all right, I'm going to factor both of these. Over here, I'm looking for two numbers that add to -5, multiply to 6, -3 and -2. Over here, I've got a difference of two squares, plus and minus 4. And then, of course, we use the zero product property to solve for x. Many of you learned if it's a simple quadratic like this, or simple factored quadratic, we just flip the signs. Okay, so, all kinds of quadratics can be solved. We even solve these graphically, right? We realize that these solutions equal the x-intercepts. Solutions for -4 equal the x-intercepts, and everything's just fine. And we start to come up with this idea that, every quadratic should have two solutions. And this idea ingrains itself, and it's a useful way of thinking of algebra. In fact, it kind of leads to the statement of the fundamental theorem of algebra, which you'll get to later on next year. But there's a problem, and the problem is this. When you've got something like x squared plus 9, how many solutions does it have? Can you factor it? Is it the difference of two squares? It's not x plus 3 times x minus 3, because if you do x plus 3 times x minus 3, you get x squared minus 9. You don't get x squared plus 9. In fact, there's no way to factor it. It doesn't factor. Can you use the square root method? All right, maybe this has a little more chance of success. So what I'm going to do to each side, I'm trying to get x alone, so I'm going to subtract 9 from each side. I get x squared equals -9. I want it to just be x, and I've got x squared, so I'm going to square root both sides. When I square root an x squared, a plus minus pops up. But now I start to have a problem, right? I have the square root of -9. What do I do with that? Well, with the numbers that humans had at this point, they couldn't do anything with that. The problem is we can't square root negative numbers, but we like this idea that every quadratic should have two solutions. I can pull this apart a little further. If I have the square root of a negative number, I know when I've got a radical, I can pull it apart into two radicals. If the two items or numbers under the radical multiply to the -9, so 9 times -1 is -9, so I'm allowed to do this. The radical 9 simplifies to 3. So I can reduce this further to x equals plus or minus 3 radical -1, but I still have the problem that I've got this radical -1. That's the problem. That's where this method seems to run into a roadblock. But humans needed a new kind of number. So what did they do? They came up with imaginary numbers. An imaginary number, the imaginary number is I. Okay, it's almost like a variable, but it stands in for the square root of -1. So you need to have this memorized. I equals the square root of -1. So back in my last problem, if I've got x equals plus or minus the square root of -9, I separate it out. I get down to x equals plus or minus 3 square root of -1. I'm going to substitute in I for the square root of -1 and say that my answer is x equals plus or minus 3i. With this new kind of number, that's a legitimate solution. Last year, when you were back in Algebra 1, you probably learned that x squared plus 9 equals 0 has no solutions. In this new universe, it does have solutions. These solutions just have an imaginary number included. This gets us to the next set of numbers called complex numbers. A complex number is any number I can write in this form, a plus bi. So b is like a coefficient of I, the imaginary number, and a and b have to be real numbers. So 17 is a complex number. It doesn't have any i's, but it's just like as if b, the coefficient, was a 0. So 17 plus 0i is the same thing as 17. So 17 is a complex number. 5 plus 4i is a complex number where a equals 5 and b equals 4. And then something with no real component but just an imaginary component, -7i, that's also a complex number. The imaginary numbers are just the part with the I. The complex numbers are combinations of real and imaginary numbers. Going to our chart, we can add our fifth and final row. Complex numbers, we've got some examples here. just reals, just imaginaries, and both reals and imaginaries. And these help us find algebraic solutions. The symbol for the complex numbers is a C, but with a kind of a double bar on the left-hand side. This chart is useful in kind of seeing which number sets are subsets of other number sets. So the natural numbers, starting with just 1, 2, 3, are a subset of the whole numbers, which are a subset of the integers. The rational numbers are comprised of fractions and the integers. The reals are comprised of the rationals and the irrationals. And all numbers combined, these are really the complex numbers, are comprised of the reals and the imaginaries.